And then let's share screen. Okay, nice. All right, nailed it. Very cool. Anyone see a full screen option? Oh, there it is. Okay, nice. And we're in business. Wonderful. Okay, so today we're going to be talking all about something called control barrier functions. So this is going to be the topic for actually your next project, which will be talking all about how we can define safety for multi-agent systems. Okay. So let's start just by introducing what topics we're going to be talking about today, and then we will go ahead and get right into it. So today's agenda, we'll be talking about a couple of different things related to this idea of safety critical control. All right. So we'll start out by defining what a safe set is. So defining safe sets. Now, once we do that, we're going to move on and talk about something called a control barrier function. Great. And then finally, we're going to talk about something called a CBF QP controller. Okay. And the CBF QP is what you're actually going to be implementing in your next project. Okay, so before we go ahead and talk about this stuff, do we have any just like general content logistics questions, where we're heading in the class, or yeah, just anything like that? How are we doing, guys? Good.
This doesn't build on anything that we've done.
This is pretty much all new. Yeah. So don't worry. You don't need to know anything else. Okay, wonderful. So with that, we can get started on defining safe sets. So defining safe sets. Okay. So a lot of the times in robotics, right, when we're dealing with these autonomous systems, we want to make sure that our systems are going to be as safe as possible, right? So we have this idea of something called a safety critical system. Safety critical system. And this is a system where safety is our first priority above everything else, right? Above, tracking a trajectory or, doing some fancy maneuver. First and foremost, safety is what we want to ensure, okay? So this could be in something like an autonomous airplane. Airplane, car, those sorts of things, right? Where human lives are sort of at stake in these autonomous systems, okay? So for these systems, what's really, really important for us is that we want to gain a provable guarantee. Provable guarantee of safety, okay? So this is sort of, I think, sort of a nice culmination of why we do a lot of proofs in this class. Like a lot of the times, I think, especially in 106A, we're always like, this theory is all great, but, I want to make my robot move at the end of the day, right? But, I don't know about you guys, but I would feel a lot better if I'm getting on this autonomous aircraft and I know someone has been like, okay, I can guarantee you, like, provably, this plane is not going to crash. I'm like, that's pretty good. I'm sort of comfortable with that idea. So what we want to do is we want to make sure we can prove in a rigorous mathematical sense that these systems are going to remain within these nice safe regions, okay? So we want to guarantee our system remains in a safe region, okay? So to do this, we're going to define a couple of different terms, okay? And the first thing we're going to do is formalize this thing called the safe region. I'm going to call it a safe set. Definition. Safe sets. All right. So this definition is going to be something that's, it's relatively intuitive, but it's nice to sort of assign some more precise mathematical meaning to some of these things. Okay. So we're going to say that the safe set, which we'll denote with the letter C, of a system is the collection of all state vectors, which, remember from earlier, that's those vectors like x and Rn that describe the configuration of our system at any one point, okay? So we're saying the safe set is the collection of all state vectors, x and Rn, such that the system is said to be in a safe state. In a safe state, okay? And I'll illustrate exactly what I mean by this just with like a little quick example over here, all right? So let's imagine that we have an obstacle. And maybe we have like our little turtle bot over here, okay? So if our turtle bot is right over here, right, this position X and Y, or let me just call it X for our state vector, then this is going to be a safe state, right? We're not colliding with the obstacle. But if instead I go ahead and I say my turtle bot is over here, right, at this X, then that is an unsafe state, right? Because we're directly in collision with that obstacle over there. So in this case, we're sort of defining safety to be like, okay, are we colliding with this obstacle or are we not in collision with this obstacle? Okay. So our safe set over here would be sort of everything outside of this region of the obstacle. Safe set. All right. So before we move on, do we have any general questions about this like concept of a safe set? Yeah, Anish.
So does the safe set only deal with like the position, or like I guess the state vector can have velocities and stuff in that?
Yeah, so the safe set is going to be based more or less on positions. So we'll talk a little bit later about how you can incorporate things like velocities into it. So this is a very simple example right over here, but say like you have input bounds on your robot and it's moving kind of quickly, then your safe set is going to depend on what that maximum input bound is. You make sure you stop before you hit the obstacle. Yeah. Yeah, any other questions? Great question. All right, very cool. Okay, so let's talk about a major challenge with this sort of safe set description. So challenge. Oh, and one more thing I just want to mention. Since this safe set is a collection of different vectors in Rn, you'll see a lot of the times written in these papers as C subset Rn. Okay, it just means it's like a sub collection. Okay, wonderful. So our main challenge with this thing is that for high dimensional systems, high dimensional nonlinear systems, the safe set, C, is very difficult to visualize, right? Very difficult to visualize, right? So in that simple example where we had this turtle bot and a little circular obstacle, right? It's no big deal. But say we have a state vector in 4 dimensions, and all 4 of those different terms in that state vector are determining if we're in a safe position or not. That's not something that we're really able to easily visualize, right? We can't really see 4-dimensional space too well. So what we want to do is we want to come up with some easy way to represent whether our state is safe or not, okay? So our answer, come up with an easy way to determine if our state X is safe. And what I'm about to write, it's sort of going to lay the foundations for this thing called a control barrier function. So for now, for what I write just after this, just think of this as like a function that indicates whether your system is in one of these safe sets or not, okay? So our main idea, here's what we're going to do. We're going to define a function. It's called H, and it goes from our state vector, Rn, to a simple scalar R. Okay, just a single scalar number. And we're going to use the single scalar number R to define if our system is in a safe set or not, according to a few rules. Okay, so define a function H that tells us safety based on H of X. Okay, so let's go ahead and sketch out sort of arbitrary safe set in 2D. I'll call this my safe set C. And I'm going to introduce a little bit of set notation that's commonly used when describing these safe sets, okay? So if we're talking about a state that is directly on the boundary of the safe set, right? Like on this little green ring on the outside, we use this curly D, like partial derivative, dc, to indicate that boundary, okay? And if we want to talk about everything that's inside that set, but not on the boundary, that's called the interior of the set, okay? So we denote that with this little int c. That's everything that's sort of inside there, but not on that very corner, okay? So that int c is going to be everything inside here. And to define this safety indicator function h, we're going to come up with a couple of simple rules, all right? So our first rule is going to be that if our state x is inside the interior of the safe set, all right, we're going to say our function h of x, our safety indicator function, should be greater than 0, okay? Now, secondly, if X is going to be on the boundary of our safe set, right, then our H of X should be equal to 0, all right? And then thirdly, we're going to say if X is not in our safe set, right? If X is an unsafe state, then our H of X should be less than 0, okay? So we have these different classifications, right? If we're in this unsafe state, then H of X less than 0, unsafe, right? If we're in this interior over here, then we have H of X greater than 0. And if we're on this boundary, right, then we have H of X equal to 0, okay? So what we're doing is we're taking this, safe set in an arbitrary number of dimensions, and we're saying, all right, we could boil down safety to a simple scalar number just using these rules over here, all right? So we're going to add a couple different constraints onto this function as well, just to give us some nice properties a little bit later on down the line, okay? So for some nice mathematical properties, what we're going to do is we're going to say our H of X should be continuous and differentiable, okay? It's going to be with respect to X. All right, so do we have any general questions about this safety function, safety indicator function? What do we think? Seem good? Cool. All right. So that'll take us nicely on to problem 1 over here. So problem 1, if you guys want to check out, this is on the discussion worksheet, or it's also posted on the website, but I'll just rewrite it down here, okay? So we're going to say, suppose we have a turtlebot with a state vec Q equals X, Y, phi, okay? So we're going to say we have our turtlebot over here, set position X, Y, some angle phi, right? And we're going to say that we have a circular obstacle over here, all right? And that obstacle is going to have center X naught, Y naught, and have a radius R naught, all right? So what we're going to say is if we consider collision with the obstacle to be the only unsafe thing, find a function H that indicates safety. Okay, so your function H of Q should be a function of the state vector over here, all right? And it should follow these 3 rules that we defined just above, okay? So what you could also assume here, just treat the little turtlebot just as a point, okay? Assume it doesn't have any radius. We'll just simplify it to make it easy for this problem. Okay, so I'll give you guys around a minute to work on that, and we'll see what you guys come up with, okay? Yeah. Oh, yeah, sure. Yeah, sure. Oh, man, that really fits in perfectly on the screen.
So regarding the definition of such a classification, still whether measures to tell whether the definition is good or not, an arbitrary definition, but whether these 3 rules could be sufficient for this kind of problem. But continuing your differentiability to such a classification, what will be
yeah, so we're going to require continuity and differentiability because we'll actually need to take the derivatives of these to get safety constraints a little bit later on, which is why those are things that we sort of require right now. Yeah, exactly. Yeah. Okay, so let's go ahead and talk about the solution to this problem. And something I actually just want to mention real quick, now that you and I brought that point up, is that if any people in here are fans of optimization, is there anyone here that's taken optimization? Cool. Yeah, so a lot of the times in optimization, you could deal with certain constraints by incorporating points where, say, your cost function will blow up to infinity. That's actually very closely related to like these functions h that we're talking about. So if you take 1 over h, you sort of get this thing called a reciprocal barrier function in terms of these control barrier functions, but in a lot of optimization literature that's used to enforce constraints and cost functions as well. So yeah, that's, I don't know, just kind of fun fact about that. But okay, let's talk about the solution to this problem. Do we have any ideas for what this function h of q might be? H of q. Any thoughts?
Well,
Mhm.
we could use the distance of the turn block.
Sure.
Obstacle.
Yeah, of course. So we could take x minus x naught. Let's just take the squared distance just to make it easy. X minus x naught squared plus y minus y naught squared minus the radius of the obstacle squared. Okay. So what we're essentially saying is that if our distance from over here to the center of our obstacle is within the radius of the obstacle, then we're going to be in collision, right? So say we're over here, then our barrier function is going to be negative. If we're over here, our barrier function is going to be positive, okay? And this, furthermore, is a continuous function of the elements of our state vector, x. Okay? So this is going to be a like safety indicator function, we'll call it. Safety indicator for our system above. All right. Do we have any questions about how we got to this point over here? What do we think, guys? Yeah, Karen.
Question about H, does it have to be this?
It does have to be continuous, yeah. Yeah, so like in an ideal world, it would be kind of nice if we could just say like, okay, it's 0 or like negative like 1 or something out there and then minus 1 in there. But we'll see why that's something we're not quite able to do in just a sec. All right, yeah. Any other questions? Cool. So let's go ahead and start talking about control barrier functions. Control barrier functions. All right, so we just came up with this function h of q that tells us all about the safety of our system, right? Now what we're going to try and do is we're going to try and apply this constraint, this h of q safety idea, to an actual dynamical system, right? So let's imagine we have a system of the form x dot equals f of x plus g of x, where x is our state vector, and then u is our input vector to our system. All right. So far, this function, right, like h of x, it tells us about safety just as a function of x. As a function of x, right? But let's imagine some sort of scenario over here, okay? Let's imagine we've come up with some feedback controller, maybe it's feedback linearizing, or it's just something like a simple PID controller that we're passing into the system, okay? That's going to be something that tells us all about this input vector u, all right? It doesn't say anything about x, it just tells us what our input vector u is going to be. So what do we want to determine if that input is going to be safe or not, right? Currently, all we have to determine safety is a constraint on x, right? Not a constraint on our input u. So what we want to try and do is, if we want to determine safe inputs to our system, we want to turn safety into a constraint on our input u. Okay. So do we have any ideas on what we might do to achieve this? Any thoughts? What do we think, guys? Anything at all? I know it's Friday. Okay. So here's something. All right. We see that our expression for x dot has the appearance of the input u in it, right? But currently we're just working with h of x. All right. So what we're going to do now is we're going to try working with h dot, right? Instead of h. Okay. Because this expression for x dot has an appearance of our input u in it. So if we want to try and find some sort of constraint on our input that keeps our system safe, maybe we can look at the derivative of our barrier function just instead of this straight up barrier function for here. Okay. All right. So before we actually involve this input, let's try and think about what a good constraint on h dot will actually be. Okay. So what is a good constraint on h dot? All right. So here's what we're going to do. let's think about the solution to the differential equation. H dot is equal to minus gamma times H. Do we remember what the solution to this thing is? Any thoughts?
Exponential.
Yeah, right. So our solution will be H of t is equal to e to the minus gamma times t times H0, right? That's H at time 0. All right, so if we go ahead and we sketch out this function, let's say we're starting at some H0 greater than 0, okay? And what we're going to get is we're going to get an exponential that asymptotically approaches the origin, right? That's going to be H of t equals e to the minus gamma t H0. So does this exponential ever cross over our x-axis over here? No, right? So it is asymptotic to h equals 0, all right? So if we're thinking about our function h in the context of safety, what this tells us is that if we start at a safe state, and we enforce this constraint that h dot is equal to minus gamma times h, we're never going to cross over into this unsafe region, right? Because we're always going to get this h of t that's just asymptotic to our unsafe set. Okay, so what this tells us is that the constraint h dot equals minus gamma times h enforces safety on our system. Enforces safety. All right. But in optimization, when we're trying to solve these different, optimization problems and we're looking at constraints, having a constraint with a pure equality like this is a little bit restrictive. All right. So what we're going to do instead is we're going to consider the constraint h dot is greater than or equal to minus gamma times h. All right. So this is less restrictive. It'll give us a lot more inputs that we can sort of look at to solve this problem. And what this is going to do is it's still going to guarantee us safety, right? Now, instead of just purely following like this little green response line over here, our h of t can be anything in this region up here, all right? So this is h of t when h dot is greater than or equal to minus gamma times h, all right? So we know we're always going to be bounded below by this function that's always greater than or equal to 0. So, just greater than 0. So this still tells us that our function h of t is greater than 0 for all time. All right. So this constraint is going to guarantee us safety and do it in a relatively unrestricted way. All right. So do we have any questions about how we arrived at this constraint over here? Safety constraint. What do we think? Seem good?
Yeah. So there's no. Could we have chosen something else for h dot to equal that would get us the same property?
Yeah. So if you just chose like h dot greater than or equal to 0, for example, and you started somewhere in this region up there, then you would still be able to get that property. But the nice thing is about this that we'll sort of see a little bit later is that the existence of this little scalar like gamma over there, that'll actually allow us to tune how aggressive we want our safety constraint to be. So this will give us a lot of flexibility in terms of what we want to do.
So okay, that's fine for the gamma, but what's special about h dot being greater than or equal to like a function of h itself?
A function of h itself.
So,
Oh, yeah. So what we want to do is we want to sort of ensure that h is always going to be greater than 0. And we want to do that in a way that involves our input, u. So we'll see how that comes around to the input in just a sec. But we can prove that if this gamma is actually something part of a larger class called like a set of class k functions or class kappa functions, then we're always going to get that greater than 0. So gamma is just one particular value that we're picking out over here. So when we have this constraint, it's called an exponential CBF. It's the easiest one to tune, which is why we're talking about it here. But yeah, it's part of a larger class. Yeah.
it's also add-on related to exponential stability.
Yeah, so it's very, very much related to exponential stability. So do you remember by any chance the homework problem on control Lyapunov functions? Yeah. So the wonderful thing about all of these control barrier function constraints and these safety constraints is that safety is really like a dual problem to convergence. And we'll see that a little bit later when we actually write out this CBF QP controller. We'll see that the form of the optimization problem to guarantee safety is almost exactly the same as the control Lyapunov function. Yeah, so it's very cool. The two of them are pretty much almost identical. All right. Yeah, any other questions? What do we think? Good. Okay, wonderful. So we came up with this constraint, h dot is greater than or equal to minus gamma times h. And now we actually want to apply this to our system, x dot equals f of x plus g of x. Oop, my pencil has stopped writing. Uh-oh. I think my OneNote crashed. All right, hopefully it's still there. Great, okay. G of x times u, perfect. My system went unsafe. All right. So what we're going to do now is we're going to try and take the derivative of this function h of x, right? So if we have h of x, right, we want to take d dt of h of x. What do we do? What's this equal to? Chain rule, right? So we're going to take dh dx, and then we're going to multiply that by dx dt, or x dot, right? But for x dot, we can go ahead and substitute in our system dynamics over here, right? So that's equal to dh dx times f of x plus g of x times u, okay? And I'm going to go ahead and expand this expression. We're going to get dh dx f of x plus dh dx times g of x times u. All right, so pop quiz question over here. Do we remember what these terms are? Do these look familiar from anything else that we discussed in the class? It was a while ago. Any thoughts? Yeah, so these are Lie derivatives, right? So this is actually a Lie derivative of our system, okay? So remember we called this LFH, right? Because we're taking derivative of h, multiplying by f, that gives us LFH. And then over here, we're going to have LGH times u. So once again, we're sort of seeing how this previous stuff that we talked about sort of ends up naturally popping up, in this new description of state, okay? So what we see in this case is that we can end up writing our safety constraint h dot is greater than or equal to minus gamma times h as L of h plus LGH times u is greater than or equal to minus gamma times h, okay? So what we've done is we've taken our constraint on safety, h of x is greater than 0, and we've transformed that into a constraint on our input u. All right, great. So do we have any questions about how we got to this point? Seem good? Great. All right, so with this definition under our belt, we could actually formally define what a control barrier function is. So definition, control barrier function. All right. So, see, a function h of x is called a CBF, a control barrier function, or CBF, if for all states x, there exists a gamma and a u such that L of h plus LGH times u is greater than or equal to minus gamma times h. All right. So what we're saying is that this function h of x is called a control barrier function if for every state out there, for every state in our state space, we're able to find some value gamma from this constraint, right? And some value of an input such that we're able to enforce the safety constraint and make sure we stay, within this safe set. Okay, great. So that tells us what a CBF is. In summary, it's just a function that allows us to enforce safety by constraining the input to our system, okay? So CBF enforces safety through input. All right. So the fact that it uses this input term to enforce safety is what gives it the name control barrier function. All right. So the barrier part talks about safety. Control part talks about the fact that we're controlling the safety through our input to our system. All right. Wonderful. So yeah, let's see. So there is like a practice problem right over here, but just for the sake of time, to make sure we're able to cover the CBF QP controller in enough detail, we'll skip to that first, and then we'll come back to this example problem if we have enough time a little bit later. All right, great. So without further ado, let's talk about the CBF QP controller. All right. So all the way earlier in the class, right, we were talking about these things called the op and off functions, and then these associated controllers called control the op and off functions, right? So just like we went from that idea of talking about something that gives convergence to something that controls convergence, we're going to talk about this sort of process of going from something that gives us safety to something that controls safety of our system, right? And this is where the CBF QP controller comes in, right? So what we want to do is we want a controller that guarantees safety of our system. All right. So what we're going to do is we're going to try and frame this guarantee of safety through some sort of optimization problem that will hopefully have a guaranteed solution. Okay. So along the way, we have a few criteria to keep in mind. Criteria for our control. One is that although safety is our actual priority for our system, safety is not the only thing we want our system to have. Right? So we might want to have other things like trajectory tracking. Right? All those other abilities that we were discussing earlier in the course. Because safety is not necessarily the only thing that we want these systems to be able to achieve. So just to think about this in terms of somewhat of a practical example, does anyone have any ideas about what the safest action for an airplane to take is? Stay on the ground, right? So that's not going to be any good for us, right? So we actually want our plane to go ahead and fly somewhere and do it in a safe manner, okay? So we want to be able to try and satisfy these other goals while we're still having our guarantee of safety, okay? So here's what we're going to do. We're going to say, suppose we have a controller K of X, right? So K of X, we put in the current state of our system, and it returns an input to our system. And this controller K of X will allow us to track a trajectory. Okay? So this is sometimes referred to as a nominal controller. Because it's saying, all right, in the best case scenario, when I don't have to worry about this safety problem at all, what would the input to my system be that allows me to track these trajectories, do all these wonderful things? Okay. So what we're going to do is we're going to form the following optimization problem. This is called a CBF QP. All right. So we're going to say the safe input to our system is going to be argmin over U in the set of possible inputs of the following. So I'm just going to write this out real quick, and then we'll talk about the different terms in this problem. U minus K of X squared subject to LFH plus LGHU MH. Okay, so here's what we're saying. What we're saying is that the safe input to our system, the best possible safe input, should be the input to the system that's as close as possible to this nominal input K of X, okay? So input should be as close as possible to K of X, while at the same time ensuring that this constraint is satisfied, okay? So what we're saying is get as close as we can to this trajectory tracking input K of X, while ensuring our safety constraint is satisfied. All right. So this is all that this optimization is saying, right? It's saying, give me the minimum, or give me the argument U that minimizes this function subject to the safety constraints, all right? And that gives us our best safe input, U safe for the system. All right. So this controller takes in an input, K of X, and returns a close but safe input. And this will guarantee that our system remains within our safe set. All right, so do we have any questions about this CBF QP? What do we think about this control? Seem good?
In the practice, how is this KX generated? Some kind of thing from, can we regard the KX as the kind of dependent?
Yeah, so KFX can really be anything in this case. So you could say generate it from like PID, feedback linearization, LQR, or even like something like MPC. So a lot of the times in practice, you can actually incorporate this CBF constraint directly into an MPC problem. And then you can get guaranteed safety through MPC that way. But yeah.
So is it the part that's highlighted that includes the other objectives you have of safety?
That's right. Yeah. So K of X incorporates everything about tracking, and we're just saying try and get close to that tracking amount while ensuring we have safety. So a lot of the times when we're not directly, about to be in an unsafe situation, it'll directly give you that tracking controller result, which means that it's going to give you safety in sort of this minimally invasive way. Yeah.
And U, I'm assuming, is some kind of control.
Yeah. So U is going to be our input that we send to our system. Yeah. So this big set U over here is going to be the set of all possible inputs to the system. So a lot of the times we'll assume that U is just going to be like Rn or something. Or in this case, for this to be a quadratic program, we assume U is a special type of set called a convex set. But that's not really something we have to worry about here. Yeah. Yeah, Kareem, what's up?
I just like this, right? Previously, convex set, does that mean that like we are sort of like traveling down that convex set is like to optimize for it? Or,
So it's that we're searching inside that convex set and we're traveling down this function over here. Yeah, so at each point in time, we're sending in our current input K of X, and we're saying, okay, freeze K of X at that level. What's our U going to be that minimizes like this little quadratic function? Yeah. Yeah, any other questions? Yeah.
Just why we are favoring the lead bracket, lead derivative here in expanding the H dot instead of directly within H dot here?
Yeah, that's a really great point. Okay, so why use Lie derivatives? Right? They always seem to get in the way, right? So you can actually put H dot in general, but we sort of risk this problem becoming not a quadratic program in this case, all right? So the great thing about a quadratic program is that a minimum will be a global minimum, and we have a guaranteed solution, okay? So the nice thing is that for a quadratic program to be a quadratic program, our inequality constraints must be affine in our optimization variable, right? So in general, if you have an optimization problem and you're optimizing over a variable U, your optimization constraints have to be of the form A times U is less than or equal to B, something like that, right? For the set of possible inputs to actually have that nice structure where you're guaranteed the solution, okay? So if we take a look at our Lie derivative formulation, right, where we have this L of H plus LGH times U greater than or equal to minus gamma times H. This is affine in our input. So when we write this out in this Lie derivative notation, we see that this optimization problem is actually a quadratic program, and that'll be something that guarantees us a solution. So really, it's a notational thing that shows us that this optimization problem will have a guaranteed like global minimum in this case. Yeah, that's a great question.
Thank you.
Sure, yeah. Any other questions? Okay, wonderful. So just a quick note about implementing these things. CBF QPs can actually be solved really, really quickly. This is one major advantage of them compared to other things like MPC, which are generally much more computationally intensive. So you can easily like run these things at a couple hundred hertz. They're able to be solved in real time, almost instantly on even very limited hardware. So in your project, what you're going to do is you're going to be implementing this in code to be run both in simulation and most likely on hardware as well. Okay, so you could just code this thing up in your favorite optimization library. In the case of the project, we're going to tell you that your favorite optimization library is Casati. And then you're going to be seeing how these things can be used to guarantee safety of many systems. Okay, great. So before we go back and finish up that practice problem from earlier, do we have any other questions about this CBF QP over here? What do we think? Seem good? Alrighty, great. So with that, let's go back and talk about problem 2. Okay. Problem 2 says that a turtlebot has the dynamics. As the dynamics Q dot is equal to X dot, Y dot, Phi dot equals cosine phi, sine phi 0, 0, 0, 1 times an input U1, U2. Okay. So let's say a CBF for this system, is H of Q is equal to X minus X safe, where this X is that scalar X, like this X over here, that is inside our state vector. Okay. It's a simple scalar function. So what you guys should try and do is, or actually, let's just say, express the constraint L of H plus LGH times U greater than or equal to minus gamma H for the system. Okay. So try and calculate what this constraint would be for this system. So just a word of advice for this one. It'll be a little bit easier to take the derivative directly as H dot in this case versus working with Lie derivatives. Okay. So try and calculate what the form of this constraint will be for this CBF and for the system over here. Okay. So I'll give you guys 2 minutes to work on this and then we will see what we come up with.
I had a question on the last page.
Yeah.
The last sentence. The last page. For a fully nonlinear system,
Mhm.
you can have a different constraint. Does that just mean negative a scalar? Negative gamma H?
Oh, yes. On the discussion worksheet, right?
Yeah.
Yeah. So for a control affine system, we're able to get that constraint in terms of Lie derivatives, and it's affine. But for a fully nonlinear system, we don't have Lie derivatives. So we just have to have H dot greater than or equal to minus gamma H. In that case, our H dot can depend entirely nonlinearly on our terms in our input.
Okay.
So it's not going to be a quadratic program, but we just have to write out the constraint in that.
So, okay, so this is not, so it is gamma times H.
It is gamma times
Oh.
H. Yeah. All right, we'll give it around 30 more seconds and then we'll regroup. All righty. So do we have any ideas on how we might approach this problem here? What do people come up with? How are we doing? Any thoughts? Mhm.
You drop X save.
Yep. Yeah, so our H dot is just equal to X dot in this case. And then where do we get X dot from?
Or, sorry, Q.
Or yeah, Q.
Oh, I see. And then, yeah, so what we're given that.
Mhm. Yeah, so that just comes from our system dynamics, right? It's going to be U1 times cosine phi. So if we want to enforce this H of Q is greater, H dot of Q is greater than or equal to minus gamma times H of Q. Well, we know H dot is U1 cosine phi. cosine phi, and that should be greater than or equal to minus gamma times x minus x safe. And that would be our constraint that we would apply to our CBF QP optimization. All right. Any questions on how we arrived at this solution over here? What do we think? Cool. Oh yeah. Yeah.
I was saying, the reason why we draw x safe is just because it's like a constant.
It's just a constant in this case, yeah. So if you had a time varying x safe, then it would stay in there. But yeah, otherwise it's just constant.
Oh, so you don't care about y.
Yeah, so in this case, we're just defining safety to be just based on x. But yeah, if we were to have it with respect to y or phi, then we would have a lot of other additional terms in there. Yeah. So I will say, when you're taking the derivatives of these h functions in practice, it can be a lot easier to take the derivative of h directly. Just look at the function h directly instead of working with the Lie derivatives, which I think can get a little bit cumbersome to compute at times, just because they're big vectors or matrices of partial derivatives. Okay. Yeah, if there's no further questions on this, I think that should be where we'll leave things off for today. We'll be releasing the next project, I believe, early next week. Yeah, I think it'll be a fun one. Should be good. Have a nice week. What's up? I think next homework is due April 18th. Yeah, and then we'll have one final homework on optimal control in RL. Yeah.
Homework should be self-contained, right?
Yes. Yeah. Yeah. All right. Fantastic.
I was you to come up to review the lectures.
Oh man. That's good. Yeah, sure. Thanks for coming.
I got a little bit confusing about it, just like that.
Oh yeah, yeah.
It's like,
Sure. Let me just stop real quick.